this video, I'm going to talk about the Adams Bashforth method. It is an explicit multi-step method, and all Adams Bashforth is formal. I'm just going to talk about the two-step one here. I'm going to illustrate it using this simple linear or initial value problem: y is equal to t minus y, and y is equal to 0. As always, we load our Python libraries, we define our function, we discretize our interval over some step n. So here I'm going to n is equal to 2, t naught is equal to a, so h is equal to 0.5, so steps at 0.5, and so our discrete steps is ti is equal to 0 plus I times 0.5, I is equal to 0 to 4. And so here we have a simple plot of it. We know the value here, but we don't know any of the values anywhere else. I chose this problem because it has an exact solution of this form. So we have our initial conditions, and then we set up our method. So the general form of the two-step Adams Bashforth is wi plus 1 is equal to wi plus h divided by 2, 3 times fti wi minus fti minus 1 wi minus 1. And note the difference between the methods of a one-step and multi-step method is you're using ti and ti minus 1, wi and wi minus 1 to predict wi plus 1. So you're using 2 bits of information now to predict the future. So that should be better. For the initial value problem that we're looking at, wi plus 1 is equal to wi h divided by 2, 3 ti wi minus ti minus 1 wi minus 1. So that's the general form of the Adams Bashforth for this specific problem. Now, let I is equal to 0, which is what we'd always do in a one-step method. If wi is equal to w naught plus h over 2, 3t naught minus w naught minus, and this is the problem part, t minus 1 wi minus 1. We don't know wi minus 1. We don't know ti minus 1, but wi minus 1 is more concern. So then what we go is, let's do the same, but for I is equal to 1. That gives you w2 is equal to w1, h divided by 2, 3 t1, w1, t0, w0. But once again, this is not solvable for the exact same reason as before. We don't know w1. We know what t1 is, but we don't know this. So to get the Adams Bashforth method working, you have to approximate the steps you don't know. So if it's 2 steps, you approximate 1 point. 3 steps, you have to approximate 2 points. Here, it's very straightforward. We have the exact solution. So I just approximate the step with the exact solution. The actual method is always only 2 lines. And it runs through the loop. And what we see here is a nice solution. Now, in the notes, you can have a look at the derivation of this. But what we have is the error is yn plus thing plus the functions plus h 5h cubed 12y dash. So rearranging that gives us, here is our local truncation error. So we solve for the local truncation error, and we now have an upper bound for our value. So we have upper bound of our local truncation error. Now the exact error is much smaller, but that's always the upper bound. In the following on notebook, I implement the two-step method for 3 different types of initial value problems: a simple linear one, a non-linear one, and non-linear one with a time component. And you can have a look at that as well to see how it is implemented.